Уступлю.
Своим, да?
Да.
Его на диван.
So what, international broadcast?
Yeah.
Yeah, they told me already about the YouTube channel, yeah?
Yeah.
So that's why it was blocked, yeah?
Probably. Он не хочет почему-то к местным подключаться, свой раздал.
Больше.
Как вообще все тяжело, да?
На солнышко.
Там же есть
Петь, а анонс вообще был, что будет трансляция?
Да,
Не
и
малая,
меня только что Юля
но она,
спрашивает.
ну, то есть, я думаю, что здесь...
Маленькая.
Она маленькая, да. Тут, может быть, туда, если большой поедет, там было бы замечательно. Почему нет? Почему нет?
Нет, кстати.
Это было бы очень хорошо, между прочим. Мы, собственно, из-за этого устраиваем здесь вот такие семинары на досках, потому что там негде.
Да, домогаться будет жаловаться, но...
Да не будет он жаловаться, но надо закрывать и экран.
За что мы все время занимаем эту комнату, но если будет хорошая доска, там...
Причем меловую ручку.
Да, меловую, хорошую, большую.
Меловая было бы идеально, конечно. Но это дирекция не пойдет.
Почему можно пойти на улицу? Надо учитывать всех.
Да выбросьте там доску большую, которая из 29-й комнаты. Выбросьте ее, которая там стоит.
А вот же вроде видео.
Это отдельно. Это вот как раз это на YouTube.
Это за запись, а здесь будет трансляция.
А там кто-то есть, кто сзади кого это делал?
Да, там Юлия Геева.
А Юлия вроде была здесь.
Потому что жила.
Так, если вот эти два...
Вот эти два. Да, мы будем здесь читать. Нет, там.
Все, наверное, начали.
Можно читать.
Ага.
Окей, слышно нас? Алло?
Hello.
Да, слышно. Отлично.
Okay, so let's start our seminar. Today we are glad to welcome back Sergey Sibiryakov, Perimeter Institute for Theoretical Physics. He will talk about effective action of dissipative systems.
Yeah, thank you very much. Yeah, and it's a really great pleasure to be here back, and thank you for all coming to listen. Please ask questions while I will be speaking. So that's a work done in collaboration with PhD students, Avshin Besharat and Yuri Radkovsky. Probably you know Yuri, some of you. Yeah, there is one paper we put out, and hopefully we'll put another one soon. So the question that we started with was inspired by teaching classical mechanics. And well, as we all know, in classical mechanics, but not only classical mechanics, especially in nature, everything we like is underlined by action principle, right? So we have this beautiful principle, which is probably one of the biggest discoveries in physics. So, well, in mechanics, let me be talking about mechanics, but of course, when we are talking about mechanics, we can always think that, we are also talking about field theory, that mechanics with infinite number of degrees of freedom and so on. So, so what this action principle tells us is that we have a Lagrangian function depending on coordinates and velocities, and the action which is integral of that, we minimize it or extremize it and get the equations of motion. So Lagrangian equations, we all know what they are. That's good, but then this is, we like these equations, but they don't describe really a large class of phenomena, which are dissipative phenomena. Yeah, so here we come and say, okay, actually in nature we always have some one or another kind of dissipation, and that is not captured by this action, by this principle. But then another class of phenomena, which probably was even more direct motivation, which is also not captured by these equations, is rolling. So motion of of a ball on a surface or a wheel on a surface, and these systems are described by they have non-holonomic constraints, what is called non-holonomic constraints. I will tell a bit more about that, and they are also not captured by this type of by the least action principle. So in that case, they are really not dissipative. They are energy conserving, but still we don't get equations for them. And allegedly, Lagrange didn't know about the existence of these non-holonomic constraints, somehow didn't think about it, and that's why he could write his least action principle. Otherwise, I think he would have trouble with that. So it's good to make not to know something sometime. Anyway, so what people do in practice? Of course, in practice, people do describe systems with dissipation and non-holonomic systems. They just add a force here on the left-hand side. Yes, so we add forces. Fi, and in the case of like simplest dissipation, this force will be, so this Fi will be, say, minus gamma ij q dot j. So that's viscous friction. So we add this force by hand. In general, these friction coefficients gamma, well, they must be positive definite, so it must be a positive definite matrix, symmetric matrix, that follows from thermodynamic conditions. In general, they can depend on coordinates themselves. So they can be functions of u. If we have more than one coordinate, especially, well, even if we have one, actually. So, a somewhat kind of traditional way also to parameterize these forces is to say that they, well, that's not really like any variational principle, but sometimes people say that these forces are obtained as derivative of the Rayleigh function with respect to velocities. And this Rayleigh function, because as I said, this gamma is symmetric positive definite, so we can write this Rayleigh function like that. Yes.
Excuse me, is Rayleigh function?
Rayleigh.
Rayleigh,
yeah.
Oh, okay.
What is the reason for appearing of such a term? Is it interaction with some other degrees of freedom?
Very good. I will come to that. Yeah. Well, in practice, it's just friction term. Yeah. So kind of damped oscillator would have this term, right?
But where it comes from?
Interaction with air medium.
Yeah, okay, I think it's a very good question. It actually goes to the core of the question. We'll come to that. Yeah, let me just say why I want, so what I want to do is to ask, is there a way to get this equation out of an action? Yeah? To have some action where I would just use variational principle and derive this equation without any artificial insertions, this additional left-hand side, right-hand side. So why I want to do that? Well, I think it's a matter of principle in the first place, but there are maybe two more concrete questions here. That action principle allows us to relate symmetries to conserved currents, to conserved quantities, so we have Noether theorem. And for that, equations are not enough. So to really have this deep relation between symmetries and currents, we need to have at least a Lagrangian. Okay, once we have Lagrangian, presumably we may have also Hamiltonian and so on, develop all the machinery of classical mechanics. And second thing we need the action for is quantization, because there we really don't know what to do if I only have equations of motion. And if I have an action, I can do path integral quantization. Now,
yeah, but look,
yeah.
expanded universe, why it's not enough like an example of what you are doing? I mean, you obtain Hubble friction from the action.
Yeah, but Hubble friction is a very special case.
You write down.
No, sometimes I'm not saying that you cannot obtain friction from an action. Some type of friction you can, but I want to obtain a general friction from the action. So say damped harmonic oscillator. Or even more. Actually, as I said, I will be actually insisting, because the question for just damped harmonic oscillator, actually the answer was known. I will describe it. But yeah, I will be insisting that these gammas will depend on coordinates. And when this can happen? This can happen, for example, in the following case. So imagine you have an object moving on a plane, xy, and moving on a plane in a fluid. Yeah? And the object, let it have a shape, non-trivial shape. And then it can move and can rotate as well, right? So it can go like linearly and rotate. And clearly, like friction in this direction will be smaller than friction in this direction. So I will have my friction coefficients will depend on the orientation of this object.
This is ij.
Yeah, this gamma ij will be well. I will have different gamma xx, xy, yy, x phi, phi phi.
Why does it depend
Where
on
is
q?
Wi-Fi?
Q is the angle, because one of the coordinates here. So this guy is described by x, y, and phi angle orientation angle.
Yeah, but it's a liquid which has an internal direction.
No. Liquid is isotropic. So for example, gamma xx.
Okay.
It depends on phi, right?
Yes.
Because. Now this is actually a simple example of a motion with a non-linearly realized symmetry, or motion on a group, in fact. Yeah. So here it may look very simple, but actually there is a group here, a group of Euclidean motions, right? So translations and rotations, and actually the phase space, configuration space of this particle is this group manifold. So this dependence on Q will always happen when I have a non-linearly realized symmetry, or when my system is moving on a group, or more generally on a coset. So what is group? So for example, or coset, yeah. So I think the simplest case of a coset is really like motion on a group. So imagine you have a group with the elements J, which can be SU2, SU3, or like that, like in this case, the Euclidean group of dimension 2. Yeah, and I parameterize it with coordinates. And we parameterize it like exponentiating the algebra, element of the algebra, where G, I are group generators, and Q's are coordinates. So in that case, like covariant object, which is invariant under the group transformations, is covariant derivative. So it's defined using the algebra element, basically this in its Cartan form, and that can be written as some Cartan coefficients depending on Q times d u j j I. Right? So these omegas depend on trivial on Q. Well, I mean for this or actually any parameterization. And the object that I have to construct is this covariant differential. So for example, covariant derivative. Covariant in the sense that it actually is invariant. In this case, it's invariant under the group transformations. Is the product of this Cartan coefficients times the normal derivatives. And if I want to preserve the symmetry, this Rayleigh function here must depend only on this covariant derivatives. So basically, this Rayleigh function in that case should be 1/2 some constant coefficients, dt ui, dt qj, and then when I open up the correct derivatives, I will get that here something non-trivially depending on the coordinates. So kind of the dependence of these coefficients, the dissipative coefficients on coordinates is inevitable in that case. Okay, so that's one example. Another example are precisely non-holonomic systems. Which are non-dissipative, as I said, but actually closely related to dissipative systems. And yeah, so let me remind what non-holonomic constraints are. So basically, these are constraints on velocities, typically linear in velocities. So apart from from the action and Lagrangian, we also have these additional constraints. Where C are some coefficients, alpha is just number of the constraint, and like defining property that these constraints are not holonomic. Yes, is that I cannot integrate them, so they cannot be integrated, they cannot be replaced by. So it's impossible to replace them by something of this form, right? And this impossibility in particular implies that these coefficient C's are non-integrable, right? So yeah, if I do this, so this is not zero.
Excuse me, Sergey, why cannot you regard these non-holonomic constraints as constraints on momenta and coordinates? Like
Yeah,
second-order constraints.
So
Just in
Hamiltonian formalism for non-holonomic system is not known. Because trying to implement this as a second-class constraint a la Dirac actually fails completely, miserably.
Where?
I think we'll better discuss it after the seminar. I mean, but it really fails almost from the very start. I think it fails because in fact, like Dirac really needs that everything follows from the Lagrangian, and if there is a constraint, it must be a constraint, due to say absence of momenta in the Lagrangian or something like this.
So you cannot add this constraint with Lagrange multiplier to the Hamiltonian action.
Yes, then you get another system, not describing rolling, describing something else. This is also known, has a name, some other type of stuff, right?
So
but if
physics will be changed.
Physics is different, yes. And there are more. Actually, it's changed qualitatively. You have more initial data. You have to provide more initial data than for rolling. Because for rolling, this literally reduces the number of constraints.
Okay, if you reduce the number of initial data, will you get back your original?
No, I think it will move differently. Yeah.
Okay.
Though this I have to check. Yeah, but I think it moves differently. Mathematicians studied that as well. Yeah.
Okay.
But that's different. Yeah. So this is okay. So we have this non-integrability condition. And how they are treated actually? How they are treated? In standard approach in textbooks, they are treated also by adding forces in here, but only in this case, the force is given some Lagrange multipliers times the coefficients of the constraint. So this is the trick. So it is treated using Lagrange multipliers, but Lagrange multipliers at the level of the equations. Not in the Lagrangian. Yeah, if I try to add these constraints with Lagrange multipliers.
I'm sorry. The constraint is the consequence of the friction.
No, here. Okay, very good.
Or not? I don't understand.
Yeah, because you are one step ahead of me. I'm actually about to say that this is not friction in principle, but it is very closely related to friction. Namely, I can get the same equations of rolling. I can get actually introducing, considering a Rayleigh function of this form.
So you get the friction from the constraint.
No, other way around. I can get constraints from friction, considering the limit of infinite friction.
Constraint from friction.
Yeah. So I can take Rayleigh function of this form, say C
Sergey,
yeah.
the question before that, why do you say that adding forces like that is equivalent to adding constant? Why do you say that? Why adding force to the right-hand side of the equation is the same as adding the constraint like that?
No, constraint as well. So you add both. You add the constraint and modify Lagrange equations with additional forces.
The additional force in the direction of the constraint, like
In the direction of the constraint, yeah.
Mm-hmm.
That's, yeah, kind of, this is called the Lagrange reaction force method, though, as I said, Lagrange didn't know about them. But
okay.
yeah, but actually I prefer to get them in a different way, as Tolle hinted. So I take a Rayleigh function in this form with some parameter gamma, and then take the limit gamma to infinity, and that actually recovers the equation of non-holonomic system. So basically you increase friction in the perpendicular direction. Yeah, it's like having a wheel, right, that like rolls like this, and I allow it to move this way as well, but with a very high friction. And then taking the limit of very high friction, basically it stop moving perpendicular to its surface. Yeah, it only can roll in that case.
So in this formalism, you don't need a constraint by itself.
No, yes, I just take this and take the limit. Yeah. Okay, so yeah, so these are two examples where dependence of these friction coefficients on the coordinates is really inevitable and crucial, and not trivial dependence. Yeah. Good. So, okay, so that was motivation part. Any other questions here?
What do you want to get at the end?
Oh. If I knew, that would not be called research. So, yeah, so now I want to get the action, yeah? And here indeed comes kind of the physical now picture, where really this dissipation comes from. Yeah, actually, let me write. I was wrong to erase it. So this is UG dot. Yeah, where does this dissipation come from? Well, it comes from interaction with something else. So basically it comes, so if I have my system, yeah, described by Q, system described by Q's, and I mean to lose energy, right, because the dissipation leads to loss of energy, it must interact with some other sector. Let's call it reservoir or heat bath. And this reservoir, moreover, should have gapless excitation. There is no energy gap in there, because if there were energy gaps, then like at low enough frequencies in the system, I could not exchange energies with the reservoir. So that is some gapless like environment, yeah, and they can interact and exchange. So the question which actually I want to ask, so in every particular case there will be some reservoir. Okay, there will be air, or there will be fluid, or there will be I don't know, some resistance in the circuit. The question that I'm asking, is there any universal description, so that I don't need to worry, to bother what is particular system that we are interacting with, what is the particular reservoir, but have some universal prescription that given this, I know how to write the effective action capturing the relevant properties of this, so that I recover the right equation. Okay. So in this case, in this sense, I want to get an effective action for a reservoir. I was not the first to ask this question, yeah, it looks like the first time it was asked, it was more than 100 years ago. But then, okay, people every 20 years, people would reinvent this model. Well, actually, there's a whole class of models. So, and the model for reservoir, yeah, and one, or maybe like people who popularized it a lot were Caldera and Leggett, who were studying effect of dissipation on quantum tunneling. So they really needed an action for that. Yeah, I mean the equations were not enough.
The coherence mainly.
And then people studied also decoherence.
But will you consider decoherence?
I will, if I have time, go to quantum effects, but there is still a lot to do there. Yeah, so it goes in different guises, this model. But typically, okay, the typical idea is to say, let me model this reservoir with a bunch of harmonic oscillators. Just as simple as that. And then couple my Q's to additional degrees of freedom that will be harmonic oscillators. And harmonic oscillators are easy enough, so we know how to treat them, and that will actually describe dissipation. So I will be using this model in the following form, which I think I saw in Caldera and Leggett, but then when I read this paper again, I could not find it, so I don't know where I got it. No, actually, I know now. But in the following form, where these harmonic oscillators are grouped into a field. So we consider, so here is time, here is one space direction, z, and my system will be living on the boundary. So Q of t is living here, you can think of it, and is coupled to a field psi living in one more dimension. This dimension is artificial, so there is no physical dimension there, but it's just convenient to get a system with gapless excitations. Yeah, so this is massless field, and specifically
It describes continuous change of frequencies in a bunch of oscillators.
Yeah, I can decompose. The oscillators come from decomposing this field into modes, right? And these modes have a continuous spectrum from 0 to upward. But now, yeah, we kind of we can package all these oscillators just in a single field.
Excuse me, this is an example, or there will be a statement that any kind of path will be described.
Yeah, that's Caldera Leggett. They have a statement. Well, I got that from the later. Okay, so yeah, so how do I write action? I write the boundary action, like original Lagrangian on the boundary at z equals 0. Then I write a coupling between these degrees of freedom and size. Yeah, actually, let me do it right away in this form. So I couple Qi to psi I at z equals 0, right? So this is taken at z equals 0. So boundary value of the field. Yeah, there is dot.
Many fields.
Huh? Many fields. Yeah. I have introduced one field for every degree of freedom. Yeah. And like standard action for, well, actually not very standard. Yeah, well, standard with here I have to put like effective metric, which is inverse to this gamma. Right. Yeah, I have to say this all works for like fixed constant gammas, right? So what I'm describing and what Caldera Leggett did and all others did, that was the case of constant gammas. Yeah, so if my gamma is constant, that do not depend on Q's, then that's the way to go. And then Caldera, in that case, Caldera and Leggett have the statement.
This is equivalent to the force F.
Right, it is, yes. So that's one statement, that I can basically take rational equations flowing from here, and I will be getting, like actually I can write them. So, yeah, so here, if I take these equations, and here on the right hand side I will get minus psi I dot at z equals 0. So it will be equation following from relation of respect to Q. And on top of that, I have standard equations for psi. Yeah? Where should I write them? Let me write them here. So box psi is equal 0. And dz psi I at z equals 0 is equal to minus gamma minus 1 ij u dot j. No, actually gamma here, right? Because I have to invert it. Yeah. So yeah, so these are the equations, And
This is the equation of motion.
that's the equation of motion, yeah. Following from the action principle, so these are variational equations from this action. So, in addition to them, I have to take the right solution. Well, as usual, the story with classical equations, I have to impose boundary conditions. And what we are doing, I mean, because psi satisfies the simple, simple wave equation, it has left-moving solutions, right-moving solutions. So I will be taking only the outgoing ones. So one moving to the right. Right, so psi will be equal to, well, it will be a function of t minus z. And and then everything works. Because then I go back and that implies that dz psi is equal to minus dt psi. I go here, I see that dt psi is equal to q dot. And then I put it back in here, which is dt psi, and I get precisely this.
So this is kind of you get, huh?
This is kind of again, well, actually in the form, I found where I found this model. It's under at Zurich. They studied for decoherence precisely. Good, but Calder-Leggett actually have a statement that as long as change in Q is small, so kind of you can treat these dissipative coefficients as constants. If coupling to the reservoir is weak it means linear response. So I mean coupling of Q to every single degree of in the reservoir is weak. So the overall coupling can be strong. So these dissipative coefficients can be large. It's not a problem. But the assumption is that this reservoir responds linearly. So we're basically in a linear response regime. So under these two assumptions, this is actually the effective theory. So any reservoir, including quantum effects, with ohmic dissipation, can be described by this model. So what are symmetries here? It's actually good to understand because we're pretending this is effective theory. The effective theory is usually fixed by the symmetries. So here the symmetries are, the symmetries of this interaction and of the bus. So I have two types of symmetries. I have psi, shift of psi, basically psi plus some constant ai, right? And that ensures that the reservoir is gapless, so that there is no mass term here. And I also have a symmetry, shift symmetry in Q. And that's also something I want, when I look here on this part, right? Because I want my friction not to break shift invariance. So it should be a kind of shift invariance. So that ensures that, this friction force depends only on Q dot in that case. Okay?
You mean the symmetry only of the interaction term of Q and psi, because Lagrange only depends on Q.
Yeah, this can depend. Well, it depends which Lagrange are right here.
Yeah.
It can be free particle, then there will be no Q dependence. But I'm worried about kind of this factor, and the coupling.
Your environment is isotropic. Is this the case?
No, not necessarily here, because this gamma ij, they need to be constant, but they can be arbitrary matrix.
Okay, so this sounds.
Good. So now I want to generalize this construction to the case of this coordinate-dependent dissipation. In particular, maybe the particular example to have in mind is this example with nonlinear realized non-abelian symmetries, that I mentioned before. And I want to preserve these non-abelian symmetries, right? So like here I preserve shift invariance in the simple case. In the more complicated case, I want to preserve non-abelian symmetries. And here there's a problem, because I cannot really, if I just try to generalize it naively, I will break, either this non-abelian symmetry, analog of this symmetry, or the shift invariance. So one or another will be broken. I can explain that. So for example...
Why?
Yeah, I think that's a good question. Okay, let me explain it. So, the way it is written now here, this dot is on psi, right? So Q, I even don't know how to generalize to preserve the symmetry. Okay, in principle, I can put dot in here, and then promote this dot to covariant derivative, but then I will break the shift symmetry inside, because this term won't be shift symmetric anymore. Yeah, and you may ask, is it dangerous? The answer is yes, it is dangerous because then I don't get the right equation. I get some non-local response.
Friction like.
Yeah, I get
forces like.
Yeah, I don't get local friction. Yeah, I get non-local response. So it looks like we need to preserve somehow all the symmetries we can. Yeah, and that's where the trick comes in. So I cannot do it with this.
Excuse me. Why don't you? Why does this thing breaks shift symmetry of psi?
Because this term is some nonlinear function of q and q dot.
Okay.
And you shift psi, and this doesn't integrate to total derivative. Yeah. Yeah. Before it was a total derivative, so it was very nice. Okay. So the idea is to. Yeah, maybe I shouldn't have a well, anyway. So the necessary step here is to first actually to dualize this psi field. Yeah, and then let me explain what I mean by this. So okay, let's come back to the case of constant friction coefficients where this works. It's all good. So we have that. We have dot here. Yeah, and the first step is to say, okay, good. Let me rewrite this action, this bulk action, as well. Let me integrate in a bunch of vectors so that I do. I think it should be like this: minus gamma ij over 2 chi mu I chi mu j. Is it by the way visible when I write it?
Take another McMaster.
This is better. Okay, so here I integrated in these vectors chi. If I integrate them out, I recover this. Yeah, it just enter quadratically. But what I want to integrate out psi. Yeah, integrating out psi will give me two equations. So in the bulk, I will have this equation. And on the boundary, I will get an equation that chi z I at the boundary is equal to q dot I. Okay.
So it is kind of momentum.
Kind of, yeah.
Why is it the derivative of psi?
Yeah.
Then you should be able to construct a Hamiltonian theory of this.
Maybe, yes. But okay, let me first do Lagrange. And then we'll talk about Hamiltonians. Okay, so this I can solve, right? Because I'm in two dimensions, so that implies that chi mu I is epsilon times the derivative of S. Right? And then the second equation implies that the time derivative of the scalar on the boundary is equal to time derivative of the coordinates on the boundary.
I mean, sine. You mean sine?
No, this is the epsilon.
This is the solution.
This is the solution, yeah. So that's the equation that I get from integrating out psi, and then I solve it, and I basically get a dual scalar field dual to this psi. Yeah. And then the time derivative of this dual on the boundary is equal to time derivative of q itself. So in fact that can be solved, and there is some arbitrariness in integration constants, but they actually engage symmetry, so I can forget about them. I can just identify the boundary value of chi with my coordinates themselves. Okay, so let me rewrite. So actually now I'm getting a simpler action.
You want to integrate out this high.
I cannot integrate out completely because that's actually reservoir. So these are these these Kepler's degrees of freedom that will be, how to say, I have to keep them. But I think, well, it depends what I want. Yeah, if I want to compute some correlation functions of my system, then I can integrate them out. Yeah, but as an action will involve them explicitly. Yeah, if I try to integrate them out, I will get non-local action at best, maybe nothing. Yeah.
Excuse me, but the thing that I didn't understand that is that you wrote an equation of motion for Xa, and you obtained a solution for Chi.
Yeah.
And, so if you substitute it into the action, you will lose the equation of motion, which is obtained by varying this Chi. How do you
No, but this, I mean, I integrate here by parts, I get 0, right? Because that's the equation of motion. So this term vanishes on shell.
So you obtain this equation by varying this side.
Which side? Yes.
And there is another equation which is obtained by varying this chi.
I mean, that will be present. When I substitute it back and take variation with respect to chi, I will get some equation. Yeah. Well, actually, the action is very simple. Look, if I substitute it, I will be just getting. Yeah, let me write and maybe it will answer the question. So here, the chi action.
Xi disappears from the
Xi disappears. Yes. So the chi action is very simple. It's just this.
Okay.
Plus this boundary condition. Yeah. So basically now I have a picture when my reservoir fields describing reservoir, they're just kind of extension of Q's of my coordinates to the bulk. Yes, it's kind of projection.
Here gamma is function of Q.
Very good. Now I can make it function. That's precisely this thing. So now nothing prevents me from making this gamma a function of chi, right? Because chi is a shadow of Q's with the same properties that this guy had. Basically the same function. Yeah, for example, in particular, I can realize on the nonlinear symmetries I want.
But then
Yeah,
you
in the
have
case of-
two independent pieces.
Well, they are dependent through this boundary condition.
Ah.
So appropriately, maybe I should write here actually chi's rather than q's. Well, basically that's action. I mean, classically, it's easy to check that, though it's not completely trivial actually. Well, I mean, before I introduce this interaction with how to say, this nonlinearity in chi, it's trivial. One can easily check that it still gives, like the right dissipative force. One can actually as easily almost check that it is true also when gamma depends on chi, because in that case, though the equation is complicated nonlinear in the bulk, it still has purely outgoing solutions. So that's basically what one can check. And given that the solutions are purely outgoing, okay, then basically the rest follows. Then we can relate boundary value of, let's say, normal derivative of chi on the boundary to its time derivative, and we recover the dissipative force. But the step we made is not trivial, because now this bulk action is not just action of free oscillators, it's actually nonlinear sigma model. So one may wonder.
This is because gamma depends on.
Yeah, because gamma depends on chi, yes. So it's nonlinear sigma model. So then one kind of sits down and asks, is it just a classical curiosity that classically I can kind of write this action, I can get the right equation of motion, but I impose, there is just some coincidence that I impose these outgoing boundary conditions, and it's coincidence that this solution exists, outgoing solution exists, and that gives me the friction. So is it just a coincidence, a curiosity, or there is more behind it? So, for example, would it make sense to take this action and quantize it? Actually, there are two questions. First one, would it make sense to take this action and quantize it? And here the answer is yes. We can take this action, quantize it, and this will describe some quantum reservoir. Okay? So the second question will be how general this reservoir is. Does it describe any reservoir as it was classically? Because classically I get the most general kind of force. Or it just describes some class. Yeah, and here, okay, so here comes the second part, actually. Let me see, I'm already talking. How much time do I have?
I think 45 minutes.
45 minutes. Yeah, okay. Good. So, right, yeah, maybe before I go to quantum, let me say that in principle, just at the classical level, so there is one more piece we can add to this section, which is actually also nice. We can add here a term with antisymmetric matrix, well, in principle arbitrary dependence with epsilon mu, so which would violate time reversal. And that actually also has a physical meaning that describes what is called gyroscopic forces. So in the classical equations, I can also add here like a term with antisymmetric form. Yeah, which does not change. It does not lead to any kind of loss of energy, but it can be present there. Yeah, for example, if something moves, yeah, if I have some magnetic dipole and magnetic field, yeah, I will have this type of forces.
Is it possible to add anything else?
No, that's it. Yeah, well, higher derivative terms on there. Yeah, yeah. I mean, two derivatives only this. Yeah.
Is it possible to remove this last term by some transformation?
No. Sometimes it can integrate. Sometimes it can be a boundary term. So, for example, if gamma is constant, then it's a boundary term. So then you, but in general, it's not.
What does it mean that you can't have anything else? You impose a symmetry. What is symmetry? You cannot add chi I squared.
Yeah, yeah. It should be. Well, if I have this, this nonlinear symmetry, then actually these two terms they take this form. Let me say gamma, and here covering derivatives.
You require gamma to be metric.
And here constant, and here covering derivatives.
So you require gamma and y to be metric and epsilon similar on the group manifold, and you impose a group symmetry.
Yes.
Then it is
Exactly.
unique.
Exactly.
Okay? And if you are just in general situation, then should you what should you say?
You mean in general? No, in general it only has a kind of sense classically. Classically, you go, you measure these two functions, and you put them.
But it is not necessary for them to be related by a group symmetry. They can be this one magnetic and this one viscosity.
No, these two are different. They are not related. No, these are different coefficients.
But what Dimas?
No, I think you said that.
I'm asking what is the statement that this is a unique, that is everything.
Yeah, good. Okay, kind of correct statement is about like the case with nonlinear symmetries. Okay.
Okay.
So in that case, my sigma model action is fixed uniquely in terms of a finite number of coefficients, which is gamma ij, constant coefficient, because here I have covering derivatives, and their form is fixed. And here I have some yij, and again here I have covering derivatives. Yeah.
Okay. And in general case, you do not have a statement that this is.
No, in the general case, look, in the general case, the nonlinear sigma model in 2 dimensions has an arbitrary function in it, right? An arbitrary metric. Okay, so that's the same, basically the same freedom.
Yeah, so what if you will add some higher derivative terms? What would it correspond at the level of the function of phi? Higher for the velocity?
Yeah, okay, maybe one thing I can say, but in fact, this is kind of the end of my note, but yeah, it's not guaranteed I will come there.
Okay.
No, I mean, any higher derivative is very, very useful, but at the level of classical equations, they don't change anything. So they don't affect classical equations.
So there will not be like higher order terms in terms of velocity?
Higher derivatives, no. No. So this model can describe only strictly onic dissipation, meaning that classical force is strictly linear in velocities.
Okay.
But they do add into quantum effective action.
Kind of theta terms?
Huh?
Theta terms? Kind of theta terms?
No, I don't know. It's some non-Gaussian noise. I don't know. Non-Gaussian quantum noise.
Wait a minute. If you add a derivative q to the fourth power, then you will get the nonlinear term and velocity from the equation, right?
No, I mean the thing you can add here will be something like mu I j k l d mu chi I d mu chi j d mu chi I l k d mu chi l
Yeah. So this will produce you a nonlinear term in velocity, right?
No, in the first no, because well, I don't know. I mean, it's easy to see if you work out, because you need to know again to see that you need to know. Well, actually, this term will okay. Yeah, I think that's the answer. So if I have purely outgoing mode, outgoing solution, this term vanishes.
Okay.
Yeah. So yeah, it will affect thermal noise and quantum noise. Yes, actually quantum thermal noise. Yeah. Good. Okay. So we already started asking. You started asking these questions. Very good. So what we want to understand next is how, I mean, what class of systems this action describes. And I think we have only partial answer to this question. But to understand, well, at least to start answering this question, we have to first understand what is possible, and how to actually formulate this question rigorously, right? And we want to get something like in the language of effective theory, right? In the normal closed systems, when there is no dissipation, we typically have a situation when we have our system of interest and some heavy degrees of freedom, right, here, that we integrate out. And then the Lagrangian, or the action that describes the low energy system, is just built using, like derivatives. So it's an expansion in derivatives, right? So the Lagrangian, say for mechanical system, it will be some potential, it will be some kinetic term, it will be, and then there will be terms with higher orders of derivatives. And so on, yeah. So this is kind of, we have a well-described algorithm how to write effective actions, effective Lagrangians.
This is the quantum mechanics.
That's quantum mechanical, yeah. So now I can do it, well, I can do it only also in classics in principle, because in fact, integrating out degrees of freedom can be done also classically, and we will also get this type of things, but so in this sense it doesn't matter. Here of course I have to implement all the symmetries properly, the symmetries of these Qs, but okay, I mean, I assume I know them. Now, actually symmetries are important because if I don't have symmetries, I will basically can get anything here. For example, these functions V's can be arbitrary. So like good case is when we really have some low energy symmetry that fixes the form of this Qs. For example, like this motion of the group, right? So let me restrict to this case. So we will be considering a case of the motion on the group from now on, since we are going quantum, yeah. And in principle, I would like to have something similar for the case of open systems as well. So I would like to, when I have this reservoir now, which is now not heavy modes, but just some, some light modes, but still I want to integrate them out and basically see what happens, right? But here things become more complicated because I'm integrating out light modes. So I cannot really write, in general, I cannot really write a local action that would, that would be a kind of result of this integrating out. So in general, this action is non-local.
Excuse me, you want to integrate out a reservoir?
Reservoir, yes.
So you want to obtain something like Lagrangian for a system with friction?
Yes, but I won't be able to obtain Lagrangian because that's basically what I'm saying. So when I have this reservoir, I think the question is which I want to kind of explain is what do we mean by effective action for open system? Yeah. And in fact, for me, I would like to mean by effective action for open system, I would like to mean precisely what we had before. So namely, some action from which I can which I can use to write path integral, and from which I can get classical equations of motion by variational principle. So in this sense, I would like to have a, some model for this reservoir explicitly, like I had classically, like for example this bulk model. Yeah. Actually, people mean something else often. What they mean, they are saying, let's take reservoir. Okay, no matter what, we don't know what it is. We integrate it out, then we go to high temperature limit. Okay, when the action becomes local, I will explain why we can hope for having local action in that case. But at the expense of having more than one field, actually, the fields are doubled because path integral at finite temperature is formulated not on an in-out contour, like we like with time, right? We have in-out. But if I have finite temperature, I have to do in-in. So I have to close this contour and consider fields living on the, or variables living on the upper half of it and variables living on the lower half of it. So the kind of standard notion of effective action for open quantum systems in this field is having a double, having some kind of action for double set of fields or degrees of freedom. Yeah, double set of variables. So how do we get it? Yeah, for this action there is a very straightforward prescription how to in principle compute it. It's straightforward, but of course very hard to implement in practice. But that goes under the name of Schwingler-Keldysh functional or Feynman-Vernon influence function. So basically we have a partition function of the system where we have a total system that has integration over Q's and some reservoir degrees of freedom. Okay, let me call them Chi's, but it's not necessarily my field. It's just just the label. And then we consider the action on this doubled contour. Yeah, we assume that the action of kind of total action, which depends both on Q's and Chi's, we assume that this is local. Okay, and then multiply by Well, basically, I have a part of the action coming from the upper contour and part of the action coming from the lower contour, and they are both in here. Split integration into like reservoir degrees of freedom and Q's I will keep explicitly, but Chi's I will integrate out. So I can always rewrite it.
You assume operator, right? At the tip of the contour. Otherwise, the contour might be like cancelled. Right?
Yeah, of course. There are some sources in here. Yeah.
You assume the source.
Well, these Q's are sources for me because I'm integrating out Chi, keeping Q's.
Yeah, but what I mean that for this path integral, there should be some operator inserted inside at the tip of the contour, right?
Well, over here, doesn't matter.
Yeah, but then you can cancel this part.
Yeah, this part can be cancelled. You're right. Yeah. No, but in fact here, of course, this total partition function is 1. Okay, but I'm integrating only under this inner degrees of freedom or this inner degrees of freedom Q's, Chi's that give me some function of Q's, and this I called influence function is in general and local. So it depends on double set of variables and also non-local in time. Okay, so the worst thing you can imagine. But let's see what we can say about it. Because what I want to do at this point, I want to see what is the general, what is the most general thing I can get, right? No, marker is good, but it's too good. Thank you. Yeah, I think it's okay. ignorance. Okay. So, yeah, so let kind of, there are different ways to address it. First one, let's consider linear response approximation. Yeah. So linear response is assumption that my system Q does not affect the reservoir too much. Namely, I can do basically like leading order, only like compute this I to the leading order in the interaction. Yeah? And yeah, for that I have to write what the interaction is. So I have some interaction potential. Yeah, and let me actually assume for simplicity that it depends on the variables themselves, but not on their derivatives. Yeah, I think derivative can be included as well, but yeah, let's make life simpler. But what I do require is that this potential is invariant under my symmetry group. Basically, if I rotate Q's and Chi's appropriately, then this is invariant. And that fixes me, well, not fixes, but actually tells me that this interaction can be expanded in the complete basis of the group, which is given by matrix elements of the representations of the group. So basically, here I have a sum over representations of the group, and over all these indices. So that's Q dependence, kind of factorized. Actually, it's analog of Fourier transform. Because, when I have a Fourier transform is the same thing for U1 group, and if I have a more complicated group, that will give all these matrices, like all the representations of the group appearing here, and then each of these matrices is multiplied by some operator acting in the chi space.
But in a particular case, you should be able to calculate this. Yes.
Yes. For SU2, these are Wigner matrices.
No, not the expansion, but in a physical problem. Do you know what we?
Yeah. Oh yeah, in the physical
this
problem.
function on the left-hand side.
Right, and in the physical problem, I know this function. Then I can expand it in these Wigner matrices. Yeah. Right. So these U's are known. Yeah. So this is known, kind of known. The known fixed by the group structure. And okay, and these are some operators. Yeah. What I know about these operators is they must implement the group transformations. I know that their 2-point functions should be diagonal. So basically, diagonal in the following way. So if I have 2-point function, so that should be diagonal in the representations. It must be diagonal in these A, B indices, which basically which are changed by the group transformations, and A prime and B prime are actually they are not touched by the group transformation. So here can be arbitrary function. K R A prime B prime T minus T2. Yeah. And here the average is taken over the thermal state of the reservoir. Yeah. So it's good. So then the next step is to take this path integral, and of using the fact that I know how the interaction look like, I can integrate out this chi degrees of freedom, leaving only 2-point, kind of restricting only to 2-point functions of O's. I'm kind of neglecting all higher point functions, assuming that they are small. So that's basically linear response idea. Yeah. We can think that there is some small parameter in here, and I'm only keeping terms of order alpha square. So that is influence functional. Well, it still looks like a mess in general. So it's double integral over time. So it's not local. But then, still the group structure helps somewhat. So I get here I get we'll explain the notations shortly. I get some terms which contain time-ordered Green's functions. I have terms which contain these unordered Green's functions. actually two more terms, which I don't write for the lack of space.
What kind of terms?
Well, the same kind. So basically, just with different Green's functions. So this is time ordered, this is unordered, then it will be anti-time ordered, and like opposite, opposite position of the operator. Yes, I mean, once it comes to this double time formalism, yeah, that's basically complexity grows exponentially. So,
excuse me, K is Keldysh function, right?
No, it's this one. Just simple correlator without any time ordering.
Yeah, but not anti-commutator.
Not anti-commutator, no. Yeah, Keldysh is anti-commutator. Okay, yeah, it's kind of related.
So Keldysh is a linear combination of G and K.
Yeah, I think so.
Keldysh is a matrix. Keldysh correlates as a matrix.
No, I mean, I'm getting, of course, it's all the same matrix. So I'm getting, so my matrix is G, K twiddle, G twiddle, and I can rotate and get Keldysh.
No, Petya, I mean that usually people work with Keldysh and time object. So this is one component of this matrix, but not this one. Okay.
Yeah, let me say what this notation is. So, okay, Q1, Q2 are Q's depending on Q1, Q2. Okay, that's what 2 means here. Plus minus means Q plus, Q minus. Yes, something from the upper part of the contour and lower part of the contour. And this minus sign means that I'm taking basically G of Q1 minus Q2 is by definition G minus 1 of Q2, G of Q1. Yes, it's parameterization of the I would say, yeah, I am getting this combination, so G Q1 times, or U of Q1 times the inverse U of Q2, and this also corresponds to some element of the group, and then denoting the corresponding coordinates by this difference. So it's kind of fixed by group structure, this part as well. Actually, this whole part is fixed. So basically here is group, and here is a reservoir. Okay, so that's kind of the most general thing. Even in linear response approximation, I'm getting a general non-local action with doubled set of fields and with arbitrary correlation functions. I mean, yeah, there is infinite amount of freedom here. And even after imposing all the group structure and everything. So to proceed, well, at least the way we see it now, we have to do something more, to assume something more, and the something more is assuming high temperature. Yeah, high temperature, well, it's actually a bit more of yeah, it's not just simply high temperature, it's actually some physics saying that at high temperature, correlation functions should have a finite extent. So basically, retarded Green's function, yeah, which describes kind of response of the system to the external perturbation, should decay exponentially. It's kind of intuitive. Actually, I don't know the proof of that. And I haven't seen, but everybody kind of using this statement. I would like to see a proof or some kind of derivation, but it seems natural. It seems natural saying that, you know, like when things are fluctuating very fast, right, with high temperature, then yeah, so high temperature leads to fast oscillations, fast fluctuations, and the memory dissipates, kind of disappears exponentially. So basically, the assumption I will be using that the retarded Green's function behaves as this, right, with some coefficient lambda. Actually, this lambda, okay, so lambda can be bigger or smaller than the temperature, in fact. So it can be, yeah, it can be bigger or smaller. And we actually do have explicit examples where it can be both bigger or smaller.
But not parametrically, right?
Parametrically. Can be parametrical.
Can be parametrically larger than temperature.
Yes, it can be. In electric,
small, some contradiction.
No, yeah, okay, let me say what that corresponds to. So when lambda is smaller than temperature, that for example, an example of that is when you have a classical retardation, right? Classical. I mean, you have some say classical, finite classical interaction time, which for example happens when you have a particle of finite size interacting with the gas, classical gas, right? So then you have some time scale of interaction of this particle with the gas, right? It's pretty like kind of crossing time. and the lambda will be 1 over this crossing time. And this is purely classical thing, so it doesn't contain h bar. And temperature actually does contain h bar and goes to infinity in the classical limit. Yeah. So opposite example. It actually was surprising to realize that there is also opposite case when this is possible, and that's the case of like electric systems or systems of fermions, electrons. Well, Fermi gas if you want, or Fermi liquid, because in that case. In that case, the crossing time actually can be much shorter than the temperature. It's basically set by Fermi energy rather than the temperature. And we can also have a like opposite case as well. Okay. Yeah. So once we have that, then things become much better because then I can, all these Green's functions, they collapse into delta functions and their derivatives. And I probably won't go through the details because that would be too much. Let me see where we come. Yeah. So doing that and going through the algebra. Response. Let me do it here. In this kind of local approximation, in fact, maybe here I should write. Let me write here. So, so as I said, in that case I can do consistent derivative expansion of these. I can do consistent expansion of these g's and k's in derivatives of delta function. And two first leading terms, I have to take them together because they are fixed by quotation dissipation theorem, so both of them must be considered at the same order. Is this. Where this rho 0, are AD are just constant coefficients. So essentially spectral densities of these operators. But then, I can substitute this form and sum over R and B. So now, actually, together with getting locality, I'm also getting, all of the sums over A and B done and kind of collapsed into a single function.
Do you have higher order derivatives?
They will be next. They will come in. And this influence function collapses into now function like integral over a single variable. Single time variable, but still I have doubled dynamical variable, right? That doesn't go anywhere. So that's integration of the delta function, and the second term is the dissipative term.
Excuse me, your action is complex. Why is it complex?
It's complex, yes. The function is complex because
you're imaginary. The first term.
This one is real. This is imaginary. Yes, it is.
So what? The action is the usual action.
It is not the usual action. That's the problem. So my problem with this influence function. No. As I said, people do call it effective action, but I don't like it.
Yeah. First of all, my first question is the usual case is in your notations is when I is real, right? No?
No. No, this is very usual. This is totally usual case.
The usual action which is real would be a real I.
No, usual action, to get from usual action to here, I would go to this double contour, integrate out something.
I mean.
Какая часть из них нормальная?
Yeah.
No, none.
Both are normal.
No. Well, normal for whom?
Can you
Not
write?
for me.
Can you write?
Yeah, let me write.
definition of
Okay,
I?
good. Let me.
Нет резервуара, Сергей.
Please repeat the definition.
Yeah,
of
if there is no reservoir, then I don't get anything. This is zero. Both. Yeah, both are zero. Because let me write actually. Okay, good. Let me write. Let me write next line. Yeah. Well, first of all, I probably should say. Okay, maybe I should not because you're not asking. Okay, what is U? But yeah, let me write next line. So if I expand up to quadratic order, okay. So at this point, I'm introducing from this Q plus Q minus. I'm going to something which is called classical and quantum fields. So, like average of Q plus Q minus is classical. Yeah, probably it will become clear why it's called this way. And the difference, actually approximately, is quantum. And the proper way is to treat this quantum as small. So next step is expansion in this quantum. Yeah, it will be clear why it's proper. So kind of leading order, Gaussian order in this Q quantum is this. So Gaussian, yeah. Let's say Gaussian approximation. Gaussian is this. dt for I over beta gamma ij qi qj minus 2 gamma ij qi dt q bar j. Now gamma is basically second derivative of this function sigma, and sigma, okay, write it here. So sigma is a function of the group, which is sum over IRAB, URAB, Q, rho R0AB. Right, so kind of some function of the group that comes out of these interactions. Yeah, and these are the derivatives of this function at 0. So here we see, so what are these two terms? Okay, they are not normal, none of them, because we haven't seen them. At least I didn't before. But in fact, they describe dissipation and noise. Now, first, why this is dissipation? Because if I take variation with, actually, classical equations here are obtained by varying with respect to this q hat and setting it to 0. So I can take variation of q hat to 0, and I will get basically here the the friction force. But at finite temperature, the beta is inverse temperature as usual. At finite temperature, there is also noise, and the noise is quadratic in q hat. Well, in fact, there is some kind of transformation where this becomes more explicit. That basically the equation following from this part of the action will give some kind of Langevin equation with noise given by inverse of this gamma. Yeah, with a Gaussian noise with correlation function given by inverse of this gamma.
You can integrate over Q hat, right?
Yeah. This is discovered Satanovich story. Yeah. Okay, so in the case of normal kind of conservative system, actually this is all 0 because there is no friction, no noise.
So e to the I, where I is the total integral, enters into the integrand of the part integral.
Yes.
E to the I.
E to the I. Yeah, of course.
Additional imaginary units.
With additional imaginary unit. Yes. E to the E to the I.
Okay. So the first term is real after multiplication by I, and the second one is imaginary.
Yes, exactly. And this one gives you Gaussian suppression basically of this noise term.
Okay.
What is что это такое? G0 или sigma 0?
Sigma is here. So sigma is a function on the group that kind of is given, that basically codes the interaction with the reservoir. But also at high temperature, you actually don't need all of this function. It's enough to know its derivatives at 0. But that's on the leading order. Okay, so I expanded this to leading order to quadratic order in Q hat. There are corrections. So I can go to next order, which is classic. And Yeah, and for that I also will able to write this expression, because this one is relatively nice. So here we get more structure. Maybe I won't write it. Okay, I won't write it completely. Okay, so there is some structure with this mu and gamma and structure constant C, structure constants of the group, Qi, Qj, Qk, Ql, and yeah, some more structure, gamma, C, Qi, Qj, Q dot K. Yeah. So that's just like next order in the Taylor expansion of this thing in Q hat. Actually, yeah, I promised to explain why Q hat is small. Okay, good. Let us look at actually the Gaussian part, because that determines the scaling of these quantities here. And yeah, the first thing is to look at this first part, which basically tells that Q at any order is a Gaussian field with certain variance. Q hat is a Gaussian field with certain variance, and to estimate this variance, I just have to equate, like this action to 1, right? So I will be saying that I have gamma over beta Q hat squared times time, but time is inverse frequency, yeah? So I will put here inverse frequency, and that should be of order 1, but I also have to recall h bars, which I set to 1, yeah? So 1 h bar, 1 over h bar is in front of the whole action, so let me put 1 over h bar. And in beta is actually h bar over temperature. So there is one more h bar. So that implies that this Q hat is of order h bar square root of omega gamma yeah, temperature is here, that's right. Right, so Q hat is really proportional to h bar, yeah, or inverse temperature if you wish. So the limit of high temperature is small, so it's kind of justified to expand it. Taylor expand. On the other hand, Q bar scaling is determined by this part. It may also be determined by the bare action, right, which we also have for this Q bar, which I didn't write. But say at very low frequencies, this one will dominate, right, because it has the lowest number of derivatives. So in this kind of diffusive limit, this term determines the scaling of Q bar, and doing the same arguments, I will find that Q bar is scales as square root of temperature over gamma omega. So here there is no h bar. So this is really like kind of classical degree of freedom, and fluctuations are classical and grow with temperature and inversely proportional to frequency, so it means things diffuse as time goes on. So yes, in this sense, there is distinction between Q bar, which is classical, that's kind of justification, and Q hat, which is quantum. So this correction that I wrote here, they are quantum, so they contain 2 more powers of h bar.
Are there any terms higher which are composed from 6Q?
Yes, there are more here.
And then the next question. Is it possible at this stage to go to the algebraic language you mentioned, to have a look what will happen there, and to return back?
You need to go to Q hat Q?
Yes.
Yeah, that will involve more derivatives. Yeah, actually I didn't say what this mu is. So mu is a fourth derivative of this function sigma at 0. So when I go to higher orders, I will get 6 derivatives.
6 derivatives, so 8 derivatives, and so on. Then you mentioned at the very beginning that it is possible to go to the algebraic language, to try to have a look whether they are exponentiated.
No, I don't think so, because this function, well, actually it's a good question, but we're probably, we're kind of looking into that, but at this point it looks like this function is quite arbitrary. So basically, well, yeah, almost arbitrary, because basically here, kind of arbitrary function on the group can be expanded in this way. The restriction that comes from physics here is that these rows are positive definite. So it's kind of not completely arbitrary function. But on the other hand, it looks like there is a lot of freedom in this sigma. So for example, like 6th derivative of it is not related to the 4th derivative. It looks like they are independent.
Okay.
Yeah, what do come from the algebra is something which I didn't write here, because here there is mu, but there is also some structure of gamma and c which is uniquely fixed by the algebra. But mu is new. But for example, this term, this one I can write. That's not long. So this one is gamma I mu, c mu, so gamma I m, c m, j k. Yeah. So this is very special structure made of dissipative coefficients and group structure constants.
So there is possibility to have a look what is the difference between group language and algebraic language, and to understand where the differences are. Okay.
Yeah. Good. So 5 minutes? Do I have 5 minutes?
More or less.
Or less. Okay, let me see. So that's quantum correction coming from here. But actually, at the same level, if I'm going to these corrections, I also have to include higher derivative terms. So I have to include higher derivative terms in here, which will have. So it has. Well, again, some structure with second derivative of the delta function and some structure with third derivative of the delta function. But importantly, these structures, they have a mu coefficient. They have something which we called rho 2ab of r. So they are analogs of this rho 0, but now multiplying terms quadratic in basically they enter in the spectral density of k with this factor, right? So they basically multiply next term in the Taylor expansion of the spectral densities of these functions k and so on, and they're in principle again new coefficients. So that, maybe I won't write the answer. One can get kind of the answer in terms of these new functions. But I think I must be schematic in that. So there is a kind of contribution to this influence functional, which comes from higher derivatives. And it will contain, so it is local integral, but now it depends on some u function. Well, it depends on the old function, sigma 0, as before, but also on the u function sigma 2, which is basically made with the same recipe from these new parameters, new coefficients. And then when I do Taylor expansion in Q's, they don't contribute at the Gaussian level, so they can only contribute at the the non-Gaussian level. But then we'll be getting something like there will be noise term, which is maybe I write it at least something, some part of it, dt, and then there is some combination depending on mu2 ijkl. So these are like force derivatives of this sigma 2. Actually mu ijkl, so first derivative of sigma, then gamma ij and gamma 2 ij, and structure constants and all that. So this, for example, multiplying this term. So this is kind of noise term. And actually there are two more combinations, but let me stick to this one. That's the fourth derivative of sigma 2, which is built in the same way from row 2. Okay. Yeah. So yeah, I think I'm heading. Okay, let me write one more term and then explain where I'm heading. Yeah, because.
So if we know the KABR, all these functions are very well known. Yes.
Which functions?
KABR.
No, they are not, because basically these are all. How to say? These are in general these are all operators.
Equal to and then some expansion, yes, or the delta function and the
Yeah.
derivative and so on. So
Right.
if I know this function, I know this coefficient, yes.
Yeah, you know deltas, but you don't know the coefficients, right? And this coefficient then
Now, if
kind
I
of
know
come.
this function, KRAB, okay?
Well, you know it if you measure all possible operators. in
Yeah,
this.
if I know this function, then I know...
Yeah, if you know this function, yes, but to know it, you have to measure all operators in this reservoir, right? Kind of all 2-point
Or
functions.
define this system.
Yeah. No, but I think here the point is that you don't need to measure all of them. What you kind of the information you need are these are these functions sigma 0, sigma 2, and eventually even not them, but higher derivative. I mean their derivatives 0, but still there are a lot of them. Yeah, I think I'm heading to this statement that let me just schematically write the other term, and this one will be like friction term, which is QI, and then higher derivative, like terms of higher order in velocities. Yeah, it will be ETQ cube. Right. So, for example, I think Sabir, you were asking about friction, which would have higher powers of velocity. It is this. Yeah, because if I take like variation with respect to Q hat, that gives me classical equation, and it gives me velocity cube. This term, this kind of corrections to friction, they come proportional to these mu2. So they don't have mu0 in them. So if I have only mu0 or sigma 0, then they are absent. Okay, so in the more general case, to the order of first quantum corrections.
But this is the effect of fluctuations. Moreover, quantum fluctuations.
No, this term is actually classical. Well, it depends on what your lambda is.
So
if your lambda is classical, this term is classical, doesn't have h bar.
But it's not like you wrote a term. You can. It's not like you introduced this term by hand. You introduced the entire path, integrated it out, and only then effectively this term appears.
Yes, that's right. Yeah. So what is let's count all the freedom we have. So we have gamma ij, which is good and something which we have anyway. These are dissipative coefficients. We have mu ij kl, which is symmetric. So which is gamma ij is symmetric, mu ij kl is symmetric, and all the indices. And we also have gamma 2 ij symmetric, and mu2 ij kl symmetric. Okay. So actually quite a lot of freedom, but apparently that's the thing. Now, the freedom is significantly reduced if I insist on ohmic friction. If I say that I don't have any contributions of force which are cubic in velocities. So then this vanishes. That must vanish. And in that case, these two vanish. Well, equivalent, I can say that this lambda, basically equivalently, that's neglecting this higher higher order expansions in the correlation functions. So basically saying that the reaction time is much shorter than temperature. Then this is out, and then everything is parameterized by one symmetric tensor and one 2-index tensor and one 4-index tensor, both symmetric. Okay, good. So one can go on, kind of make more analysis. But let me actually recall where I started, and I started from this model with the bulk action, yeah. And now the way to actually understand, so basically the way to understand whether this bulk action describes everything or not is to say, okay, good, this is kind of everything, yeah.
Тряпочка там чистая рядом не лежит?
Лежит. А что?
Стирает.
Тут скорее вот жидкость.
Такой маркер просто.
Ну, грязная очень тряпочка. Грязь размазывает.
Окей, вон тряпочки.
Где? Вот она.
Yeah, where I was. I was saying that. That basically why we did all this. Well, okay, it's good. It's interesting on its own. So basically, that's the most general influence functional. Thank you. The most general influence functional we can get. Actually, ever within linear response. But we can also basically recall at this point that we started with this bulk model, and we can ask, so what if I take my bulk model, integrate out the bulk, do I get this most general thing or not? If I do get the most general thing, then basically this is an effective action for arbitrary, quantum reservoir, at least at this, with this assumption, with these qualifications, like high temperature and the first quantum correction. Or I don't get it, and let's look at the bulk model. So the bulk, let's just compare the freedom. So in the bulk model, I do have this gamma, definitely, and this is this part.
So here you assume that generic bulk model describes you generic friction.
Actually, I'm not assuming. I want to test it. I want to see if this generic bulk model will give me general friction or not, or general dissipative influence function.
So you asking whether you can obtain any influence functional starting from the bulk model.
Exactly.
Okay.
That's the question. Okay, good. So that's what I have, like originally. So here I have only gamma. And this gamma matches to this gamma. Okay, I call them the same name, but actually I can go and now integrate out chi's at high temperature. So I basically do the same. Well, not the same, but I'm doing this. I'm doing an explicit calculation of influence functional at high temperature in this model. And actually, the Gaussian order, I actually do get the most general Gaussian integral influence functional because basically I cannot get anything else. I mean that probably was already clear when we came here that this is the most general thing we can get. And yes, with the bulk model, we do reproduce at the Gaussian order. We reproduce everything. Well, Gaussian order here means basically classical order, but now classical statistical, and that's something more compared to what was there before, because now in this statistical, machinery, we don't impose outgoing boundary conditions. We impose honest thermal, like density matrix in the initial state, which actually implies that the quantum field is purely incoming. And due to quite non-trivial, properties of the equations, we can solve them and get local influence functional. Because I think the main kind of thing which was not obvious, that in this bulk model we'll get a local functional. Because there is interaction, but it's not a very strong interaction. But we do get local influence functional, and that precisely reproduces this. So at the classical level, this is the most general thing. Now at the quantum level, clearly I don't get this mu, right? I don't have this freedom. But I can add it, and that actually is higher derivative terms. And actually that's the only thing I can write, because if I try to write something else, for example, more derivatives acting on a single field or so on, I can reduce those terms to this one by using integration by parts and equation of motion. Okay, so actually equation of motion from the linear part. Here I'm basically writing. In the bulk I'm really writing honest effective field theory as we know it. So basically I'm adding all possible terms with higher derivatives, which are consistent with the symmetry, and eliminate the terms equivalent up to equations of motion. Okay, so that's the most general one. And this nu indeed maps to this nu. In fact, here, if you look kind of carefully, actually here there is even more freedom than here. Because here mu was totally symmetric. And here nu need not be totally symmetric. So nu is only symmetric in the first pair and second pair, and it is symmetric under interchange of the pairs. but this is less symmetry than here. So how come? And the answer is that this is actually the most general case, because this derivation I did before was within linear response. Beyond linear response, this mu need not be totally symmetric. And how we know that? We know that because we can write the most general influence function using basically a flotation dissipation theorem. Yeah, so the most general influence functional compatible with flotation dissipation theorem actually contains as a freedom a tensor of these symmetries. Of course, as long as I insist on purely ohmic dissipation. Yes, so with ohmic I also have this term as well. Okay, so what? So where do we stand? Well, basically, yeah, we have two types of results. So one result is basically a classification of influence functionals, within kind of the most general one, and then various reductions of it, reduction to linear response or reduction to ohmic dissipation. Yeah, at high temperature, okay, with the first quantum corrections. On the other hand, I really don't like these influence functionals because it's a mess to work with. I mean, they have double the number of fields, and when you start computing something with double number of fields, at least to me, it always looks like, immediately looks like schizophrenia. So you have these two fields, and then you have all this multiplication of Green's functions. Yeah, I mean, very hard to compute. Only Yuri can do it. So I prefer to have really like something which I understand as effective action, and for that we have this bulk model where basically, and we have kind of general recipe. If you want to write effective action, and you know your system on the boundary, write the sigma model with the same symmetries, and at least, well, at the classical level you will get, at the classical statistical level you will get the right answer, the more general answer, and and you will also properly reproduce inclusion of first quantum corrections. Question is, what happens next? For example, do we reproduce further corrections, and in particular, can we resum them if we go to low temperature? And that's not clear. Yeah, whether we can basically have this bulk model as effective model at all temperatures, or it's only kind of high temperature approximation. Yeah, other questions here are actually would be nice to have some signatures of these quantum terms, you know, like to go and measure, because yeah, we predict kind of general relations between them. They're actually quite complicated, these relations. There is a lot of freedom, but still there is a relation, yeah? There are relations. So if one could measure like enough observables, one could test these relations. I just don't know at this point whether it's possible to measure those observables or not. Yeah, let me see. Oh yeah, another thing, by the way, here I was assuming, actually, throughout, I was assuming, well, in the second part of the talk, I was assuming time reversibility of the dynamics of the reservoir. In principle, one can generalize the whole story to time reverberating interactions. And that's also interesting because that could describe various magnetic effects, presumably, or spin effects. And yeah, would be good to generalize it to field theory. Well, in principle, it's straightforward because I mean, in field theory I would do just the same, but field theory may impose additional restrictions, for example, relativistic invariance. Yeah, and it may not be always obvious whether kind of the general construction, you know, how to make it compatible with these additional symmetries. Yeah, for example, for hydrodynamics, I can say that, okay, we can describe, using this formula, we can describe hydrodynamics, for example, like Navier-Stokes equation, non-relativistic one. So that's quite, I mean, incompressible fluid, that's quite straightforward. And here there's a question whether we can say, whether this framework helps to say something about turbulence. I don't know. But if we try to apply it to relativistic fluid, that becomes a bit trickier. Actually, people have done something along these lines of this influence function for relativistic fluids, but to me there are a lot of questions there.
Actually, there is what I had that an important problem in cosmic rays, for example, okay, is they want to solve Boltzmann equations for kinetic equations for this cosmic rays, how they drift inside the galaxy. But it's important to impose a condition that the light call condition, right? That causality, and there are no causal. They don't know causal. Boltzmann equation.
Yeah. It's also true for hydrodynamics precisely. For relativistic hydrodynamics, if you try it, if you start doing it naively, you start getting like a causal signal kind of propagation.
What do you mean? Hydrodynamics, for example, near the black holes, like in the jets, like.
Yeah. It is a causal. Yes. I mean, if you just take the equation from model Lipschitz, they are a causal.
Yeah, but so this is a problem.
This is a problem.
Okay.
Yeah. So this, I mean, there's a hope that this approach could help to solve this problem, but it's not real. As I say, it's not. For example, I don't know at this point. I don't know how to directly apply this kind of to write the effective action, or I mean, the bulk model for relativistic fluid. Yeah. There are some ambiguities because it's compressible necessarily, and the kind of this compression mode is not fixed by any symmetry. Or at least I don't know the symmetry. Yeah. Thank you. Thank you very much.
Thank you. Questions?
Is this S is a two-dimensional field theory?
No, this one. This is two-dimensional field theory. That's right. Yeah. This is the bulk action. Yeah. Mm-hmm.
Similar question: is DGP can you interpret DGP as a gravity restriction? And what about
no? But it's very close. Yeah, this is kind of very similar to DGP. Yeah.
So, what will be your interpretation of five-dimensional Planck constant, etc. In these terms, in these effective terms, like gravity restriction?
No, I mean here it's quite important that I add only one extra dimension. I mean it's two-dimensional.
Okay.
And kind of the action is how to say? I mean, kind of this Z and T they enter at a different footing from X's, right? That would be there.
Right.
Yeah. So I mean that's different from DGP because they want to treat Z and X the same way. They just have the brain, and then the bulk action is completely Lorentz invariant, right?
Okay.
So all these are treated equally. In my construction of hydrodynamics, for example, I would treat them differently.
Are the integral over X and that's it?
No, integrals, yes, but I mean, how do you contract the indices? I mean, do you insist on kind of Lorentz invariance in all directions, or only in these two?
You mean if you really write gravity restriction, you want to propose a breaking of Lorentz, like
and that makes it hard because the gravity. I mean, I don't know how. Yeah, I mean how to break basically symmetry between X and Z in gravity.
Okay.
But
so this is not generic. Nevertheless, you can interpret it as a
no, that's what I'm saying. I mean, the kind of an open question is what to do when your system has additional symmetries. Kind of this framework may not be straightforward in that case, or maybe fail at all. I don't know. But yeah, so far I was not assuming. Well, I was assuming only that my system has this nonlinear Rayleigh symmetry, nothing else. No relativistic invariance, no diffeomorphism or something. I think in many cases you can implement those kind of additional symmetries, but it hasn't been done yet, and in some cases it's not straightforward. Yes.
Any questions? If there are no questions, let's end the speaker again.